Hello students, welcome to class 12 physics class. Today we discuss a last part of this chapter, alternating current and electrical machine. So today's class we started with a new topic, that is LC oscillation. In last class we discussed about the LCR series circuit, that means the inductor, capacitor, resistor. These three are connected in series with a AC source. Now today we discuss about the LC oscillation. Actually, this circuit is constructed with an inductor and a capacitor with a both are constructed with an inductor and a capacitor. But why we say is that LC oscillation, after describing this method you can understand why we call this is a oscillation. Okay, so let's start. This is the diagrams. 10 diagrams are there. 1 2 3 4 5 6 7 8 8 diagrams are there to explain the total procedure. So when a charged capacitor is allowed to discharge through a non-resistive inductor, electrical oscillation of constant amplitude and frequency are produced. These oscillations are called LC oscillation. So whatever the oscillation is created, that is in this circuit which is contained the inductor and the capacitor. That's why that oscillation name is LC oscillation. So I will explain this first. First, in this circuit you see that initially the charge is connected with an ideal inductor. A capacitor is connected with an ideal inductor. So the electrical energy is stored inside the charged capacitor. We know that the capacitor stored the charge. Okay, so first a capacitor with some initial charge, it is connected with an ideal inductor. So the electrical energy stored in a charged capacitor, that has some value, and we know that value is half q square by c. We know that u equals to half q square by c, and as there is no current in the circuit, the energy stored in the magnetic field of the inductor is 0. There is a no current. That's why I equals to 0. Because at first what happened, the capacitor is charged by the battery. Okay, whenever it will be charged by the battery, then we replace the battery by an inductor. So after that, so inductor is connected with a charge. So in that case, the capacitor does not discharge any charge from it. That's why if the charge is not moving, or if the magnetic flux if not linked with an inductor, it will not induce the electric current. So first figure we get electric current will be 0. Now as the circuit is closed, second number figure, the capacitor begins to discharge itself through the inductor. Capacitor, it will whenever it will this is a very first process. Okay, first we replace the battery by an inductor, then whenever it will connected, the capacitor start discharging. So in first figure, suppose there is a 4 positive charges. After discharging, it has now 2 charges. So it will discharge through the capacitor, through the inductor, and due to that, whenever the current is moving through the inductor, from the electromagnetic induction, self-induction and mutual induction, a magnetic field related with a coil also be changes. That's why it will induce or it will cause a current I through the circuit, and its direction is C to L. As the current I is increases, how it will increases? Because after some time, because two charges are present inside the capacitor. After third figure, that 2 charges also be discharged from the capacitor. So the value of the I or the magnitude of the current in the circuit also be increases. So as the current I is increases, it builds a magnetic field around the inductor, and a part of electric energy of a capacitor gets stored in an inductor in the form of magnetic energy. Okay, at a later instant, what happened? The capacitor gets fully discharged. Third number figure, you see that the capacitor gets fully discharged. No charge is inside the capacitor, not a single charge is present. So in that case, the inductor has a strong magnetic field is created or builds around the inductor. So the whenever the capacitor gets fully discharged and the potential difference across the plates becomes zero, the current, so in that time we can say that whatever the current is produced or built in the circuit, that is the maximum current, because capacitor has no charge. Whatever the current we get because of the discharging of capacitor, now capacitor has no charge, so whatever the current is built up in the circuit, that is a maximum value, and that's why it is denoted by I naught. Now, thus the entire electrostatic energy of the capacitor has been converted into magnetic field energy of the inductor. We can say that total capacitor energy of a capacitor is converted into magnetic field energy of the inductor. Okay. Next procedure. After discharging of capacitor is completed, the magnetic flux linked with the inductor decreases, because no charge is discharged from the capacitor. Capacitor has zero charge. After that, its magnetic flux linked with the inductor become reduced. It will start decreasing and inducing a current in a same direction. You see that the direction is same. First, capacitor charge, because we know that the current direction is positive to negative. So C, from whenever it will discharge, the current direction also be same from positive to negative, C to L. After that, after fourth figure, whenever the capacitor is zero charge capacity, so the magnetic flux linked with the inductor, it will becomes it will decreases. So whatever the current it will induce, that is also in a same direction. The current thus persists through the decreasing magnitude, and that current means due to the decreasing of magnetic flux linked with the inductor. So that current charges the capacitor in a opposite direction. Here you see that the lower part of the capacitor get positive charge, but in a first figure you see that the first plate of a capacitor, it is a positive charge. Okay, so after completely fully discharged, after fully discharged, a capacitor gets fully discharged, then due to the decreasing of magnetic flux linked with the inductor, it will cause the same direction, it will induce the same current in the same direction, and it will charge the capacitor in a opposite direction. Okay, after that what happened? The magnetic flux again it will reduce, the reduce, and the charge, it will charge the capacitor plates. So in figure E, you see that the no magnetic flux is linked with the inductor, and the capacitor plate is fully charged, but in a opposite way, in opposite direction, that with compared with the first figure. In first figure, first plate is a positive, second plate is a negative. Here the negative lower plate is a negative, and the upper plate is negative, negative, lower part is positive. That means the direction is different compared to the first one. And this figure E, the inductor lost all of its magnetic flux. Magnetic flux linked with the inductor is zero, and the capacitor is fully charged, but the charge with the polarity opposite to the initial state. Now what happened? The capacitor begins to discharge again. Now in this case, the capacitor sent the current in an opposite direction. This is figure F. Sent in a opposite direction, and whenever it will discharge, sent means discharge, it started discharging. So whenever it will discharge, again the magnetic flux linked with a coil linked with a inductor, and it will set a current in the opposite direction. In that this way, when the capacitor gets fully discharged, so the magnetic flux linked with the coil, that is a maximum, so it will set the current in its maximum value, that is I naught, but in a opposite direction. After that, figure 8, what happened? Whenever the capacitor C, it's fully discharged, then the magnetic flux linked with the coil decreasing, and due to that the capacitor plate again it will charge, and this time the charge will be same with the initial state, that is for figure A. So like this way it will work. Like this way, once the capacitor gets fully discharged, where 0, but the inductor has maximum value, so the one current direction is the one, suppose the left to right direction. After that again capacitor gets charged, inductor fully 0, but the current direction is same. Now second time when the capacitor discharge the charges, the current direction is opposite to the first from the first case. Okay, and then again the inductor, inside the inductor magnetic flux is linked, then the capacitor fully discharged, then again the in after some time the capacitor will charge and the inductor will fully magnetic flux zero magnetic flux is there. Like this way it will happening. Thus the energy of the system continuously surges back and forth between the electric field of the capacitor and the magnetic field of the inductor. This produces electrical oscillation of a definite frequency. It has some frequency. It creates an oscillation. Sometimes that means the charges move, first of all move from C to L, then again that means left to right, then again right to left, left to right, then again right to left, like this way. That's why this is called LC oscillation. And if there is no loss of energy, the amplitude of oscillation remains constant. Such oscillation are called undamped oscillation. Such as undamped means energy is constant. If energy is constant, no loss of energy is there, then that oscillation is called undamped oscillation, and that's why this is called LC oscillation. And but LC oscillation mainly usually it is a damped, because every inductor has some resistance, that is a inductive reactance. This causes the energy loss as heat, and even if the resistance were 0, the total energy of the system would not remain constant. It is radiated away in the form of electromagnetic wave. In fact, the working of radio and TV transmitted is based on such radiation. That's why the LC oscillation is not the undamped oscillation. There is a few amount of energy will be lost. Clear? Okay, next the electrical machines. You actually you know these things. Again, just recall these things. Transformer. Transformer, what is a transformer? It is an electrical device. It converted electrical current, alternating current at a low voltage into that high voltage, or vice versa. We use the transformer to increase its voltage, the alternating current at low voltage to high voltage. So if it increases the input voltage, then it is called step up transformer. If it decreases the input voltage, then it is called step down transformer. Okay, this is a two diagrams for transformer, laminated iron core. A and B. A is a step up and B is a step down. This diagram is little bit different. You see that in this figure, the wiring in the first AC source, which is connected, for that is primary and secondary. These two are different for different figure. Okay, so if we increase the input voltage, then that transformer is called step up transformer. If it will decrease, then it is called step down transformer. And we know that the principle, that is a mutual induction. When the changing current is passed through the one of the two coupled coil, and induced EMF is set up in another coil. And if we discuss about this construction, and P and S is written, P is the primary, S is the secondary. The transformer mainly consists with the two coils of insulated copper wire having different number of turns and wound on the same soft iron core. The coil P to which electrical energy is supplied, that is called primary energy, and the coil from which energy is drawn or output is obtained is called secondary. To prevent energy losses due to the eddy currents we studied electromagnetic induction, a laminated core is used. That's why we use the laminated core to avoid the eddy current. Because of high permeability of soft iron, the entire magnetic flux due to the current in the primary coil practically remains in the iron core and hence passes fully through the secondary. This also this also prevents the stray currents being generated in the conductors lying around and consequent power loss. There are two types, another two types also be there. One is a core type transformer. In this type of transformer, the primary and the secondary coils are owned on separate limbs of the core, so that the core is largely surrounded by the coils. Another one is a shell type. This type of transformer, the primary and the secondary coils are owned one over another, and this coil is very largely surrounded by the iron core. Transformer used in radio and TV transmitter and receiver are of cell type. Okay. If we discuss about the working principle, the alternating current, because alternating current AC current is it's supplied to the transformer, and alternating current flows through the primary. It generates the alternating magnetic flux in the core, which also passes through the secondary. This changing flux set up an induced EMF due to the mutual induction in the secondary. Also a self-induced EMF in the primary. If there is no leakage of magnetic flux, the flux linked with each turn of the primary will be equal to that linked with each turn of the secondary. Now the theoretically how we can explain, we consider here there is no load current. Load is connected. Load means through which we can obtain the output. So first of all, we consider there is no load is connected to the secondary. That means terminals are open. Here the load is connected. To load, it's written over there. To load means any resistance, any electrical device is attached over there. So no electrical device or nothing is attached over there. So the terminals are open. And we consider the N1 and N2 are the number of turns in the primary and the secondary coil. So the induced EMF in a primary coil from the electromagnetic induction, E equals to minus N into d phi by dt. So E1 equals to minus N1 into d phi by dt. Now induced EMF in a secondary coil, E2 equals to minus N2 into d phi by dt. Phi means the magnetic flux linked with each turn of the primary or secondary at any instant. Thus, if we divide this two equation, E2 by E1, we get N minus cancel, so N2 by N1. This is one relation. And if E that is a applied EMF to the primary, by Lenz's law, self-induced EMF E1 opposes E. In a primary coil, we know that the self-induction, whenever the current is passes through the inductor, it will create a magnetic flux around it and it will opposes the applied EMF. It will generate a back EMF which is opposes the original or the main EMF. So if we consider that E1 is the self-induced EMF in a primary coil, so it will opposes the E, which is the applied EMF. So the resultant EMF of the primary, that is E minus E1. Always E is greater than E1. So E minus E1, that is the resultant EMF in the primary. This EMF is sends current I1 through the primary coil of resistance R. So we can write E minus E1, that is equals to I into R, I1 into R from the Ohm's law. But that resistance is very small, so the term IR1, that can be neglected. So we can write E equals to E1. Thus this E1 may be considered as the input EMF and E2 as the output EMF. So we can write E2 by E1, that is equals to N2 by N1. And this ratio N2 by N1, this is the number of turns in the secondary to the primary. This is called turns ratio of the transformer. It is also called transformation ratio. Okay, in case of a step-up transformer, N2 is always greater than N1. The turns in a turns ratio is greater than 1 and therefore E2 is greater than E1. The output voltage is greater than the input voltage. In case of a step-down transformer, N2 is less than N1, so E2 is less than E1. So the output voltage is less than the input voltage. Okay. And if we want to find out the current expression, this is a EMF expression with the number of turns. If we want to find out the current expression, so we can write that if we assume that the transformer be ideal, that means no energy will loss. So input power equals to output power. Whatever the input we given, we get the same amount, that is in terms of output. So we can write E1 I1, power means E into I. So in input, that means a primary coil. So E1 I1, that is equals to E2 into I2. I1 and I2 are the primary and secondary currents through the in the primary and secondary coil. Now so we can write I1 by I2, that is equals to E2 by E1, and E2 by E1, that is equals to N2 by N1. So we can write I1 by I2, that is equals to also N2 by N1. This is the another one relation. And if we find out the efficiency of a transformer, efficiency is defined as eta, denoted by eta. Eta equals to power output by power input into 100%. Always the efficiency is counted as a output by input, power output by power input into 100. The efficiency of real transformer is fairly high, through not 100%. It is 90 to 99%, but not no electrical device has a proper efficiency, 100% efficiency. It is not possible. There is some amount of energy also be lost. The main cause for the energy loss in a transformer, that is eddy current loss, flux leakage, copper loss. Due to these things, the energy will be losses. That's why it is not that 100%, but near about it, 90 to 99%. There are many ways we can use the transformer. One is for voltage regulator for TV, refrigerator. We can in stabilizer power supplies. Step down transformer used for obtaining large current in a electrical welding. In an induction furnace, we use the step down transformer. Step up transformer used for production of X-rays. It is all these things is written over here. In loudspeaker, telephone, receiver, we use the small transformers. Okay, and this is some numericals which is related to that expression. E2 by E1 equals to E1, N2 by N1, that is equals to I1 by I2. Just you go through this to then next one is a AC generator. You also studied in class 10. If you want, then you can go through my YouTube channel, and from class 10 you can in a chapter magnetic effect of electric current, and from that chapter you can get the video of this AC generator. I can explain with a diagram. Here also I will explain, but the proper way we can explain if you want, and then you can please once you visit. So AC generator, or it is another name is dynamo. So generator, it is a device which convert the mechanical energy into electrical energy. And AC generator, it is work on the principle of electromagnetic induction. And using the Fleming's right hand rule, we can find out in which direction the coil will rotate. Generator, this is the diagram of the generator. Actually it is constructed with a many construction is there. Two field magnet for permanent magnet, north pole and south pole for the magnetic field. And here PQRS, that is the armature. It is consist with a rectangular coil, consists large number of turns of insulated copper wire on a soft iron cylindrical core. Third number is slip ring, S1 and S2. These two are the slip ring. It is connected with the armature coil. This ring is mainly fixed to the same shaft which is used to rotate the coil. Next, B1 and B2, these two are the brushes. To graphite or the flexible metallic rod called brushes are lightly pressed against the two slip rings. The brushes B1 and B2 remains fixed in their position and maintain the sliding contact with the rotatable slip rings S1 and S2. Just it will use to reverse the direction. Okay, another one is a source of energy. The armature of the coil is rotated about its axis with the help of a turbine. At the outsider we use axle, or the axle it is connected, through which if we rotate it will due to its rotational kinetic energy of the turbine, which is ultimately converted into the electrical energy by the AC generator. We know that the armature, if the armature is coil is rotated, that means PQ coil in upward direction and RS coil is side is downward direction. Using the Fleming's right hand rule, we can understand in which direction the current will induce, because the magnetic flux linked with this coil will be changes when it will rotate. Okay, as the armature of the coil rotates, the magnetic flux linked with it changes, so it is induced the current flow through it. So if we consider the PQ side, so you stretch the Fleming's right hand rule. You stretch the thumb, forefinger and the middle finger mutually perpendicular to each other. Then the thumb will represent the force in which direction you move, force in upward direction. Forefinger it will represent the magnetic flux, so the middle finger represent the induced current direction, and we get the induced current direction is P to Q. Now in R to S you get the current direction is R to S. Now after half rotation, after one rotation, PQ, when the PQ goes the downward direction and RS in outward direction, the current direction also be reversed. In that time the current direction in PQ it will be opposite to the first one. Like this way this will work. And if we want to find out the expression of the induced EMF, that is whatever n equals to the number of turns, A is the area of phase, B is the magnitude of the magnetic field, and theta is the angle which normal of the coil it will make with the B, and omega is the angular velocity of the coil. So we know that phi equals to NBA cos theta, that is cos theta means omega into T, so NBA cos omega T. From the Faraday's flux rule, E equals to minus d phi by dt. So if we place the value of phi over here, after differentiation we get NBA omega sin omega t. And NBA omega, this is represented by E naught. E naught equals to NBA omega. Okay. So this is a maximum. E naught is a maximum value, a magnitude value of the EMF. Okay. And if we want to find out the current expression, I equals to E by R. E means E0 by E0 sin omega t by R. So E0 by R, that gives us the I0. So we see that the both voltage or the EMF and the current both vary sinusoidally with the time. Yeah. Okay. And there is some advantages and disadvantages also be there, because the generator we get two types of generator are there, AC generator and the DC generator. So maximum time we use the AC generator, because generation of AC is more economical than the DC. The alternating voltage can be easily stepped up or stepped down by using the transformer, but in DC we cannot. uh, AC can be easily converted into DC by using the rectifiers. Another one, the alternating currents can be reduced using the choke coil, but that is not included in your syllabus. Okay, but there is some disadvantages also be there. AC, the peak value of AC is high. That is IRMS equals to I0 by root 2. It is dangerous to work with AC. The phenomenon like electroplating, electro-refining, typing, this is cannot be used. For this we use the DC direct current. These are the disadvantages of AC over DC. Okay, so this chapter is completed. Thank you very much. If you have any problem, please write in a comment box. Have a nice day. Tata.